Hi, and welcome back to Codex. Our speaker today is Yousef Qaddura, who is a graduate student at Ohio State. Yousef's research exploits symmetries in data to improve machine learning algorithms. Today, he'll tell us about weighted phase retrieval. Take it away, Yousef.
Thank you for the introduction, Emily, and thank you for the organizers for the invitation. So today I'll be talking about stable weighted phase retrieval. Some of you might be familiar with standard phase retrieval, and you can find this as a natural mathematical generalization of it. And whether you're familiar with standard phase retrieval or not, I'll still motivate the problem with a cat. I will go a bit fast in the motivation because the rest of the talk will not depend on it. But let's get started. So I have a video of a cat that's rotating, and I'm gonna hold a camera to this video, and I'm gonna take 2 pictures from the front and 2 pictures from the back. Now, this camera that I'm holding has an issue. It adds IID Gaussian noise at each pixel. So these grayscale images from now on will have noise added to them because of the camera. And when I was taking the pictures, the camera could have been tilted. So some of these pictures could have been tilted. My goal is to get rid of noise. In particular, I want to get rid of noise in the top left picture. And the law of large numbers tells me that I can average noise out to get rid of it. So if I think of these 2 images as having the same origin, I'll be like, okay, let's average them out. But that's a bad average to take because the cats are being messed up with each other. And when you take the average, you get a picture of 2 cats instead of 1 cat. So a better thing to do is to get rid of the tilt implicitly and rotationally align the 2 pictures as much as you can so that the cats align with each other as much as they can, and then take an average. Now, it's a better average. The white fur is getting overlapped with the white fur, black fur with black fur. So overall, that's a better average to take. But then 2 questions arise. What do I mean when I say rotational alignment? What does that mean mathematically? And which pictures do I choose for averaging? For example, if I grab the picture from the back, that's a bad average to take. But even after I do rotational alignment, this is still a bad average to take. I'm losing white fur because it's being averaged with black fur. I'm losing the eyes because they're also being averaged with black fur. And parts of the cat are being averaged with noise. So there's some overlap that we don't want to take place. So in some sense, these 2 are nearest neighbors, and these 2 pictures are far neighbors even after you do rotational alignment. And I'll make that more mathematically precise, but I just wanted to mention that this problem is a real-life problem called Cryo-EM, Cryogenic Electron Microscopy, where you take pictures of a molecule, the pictures are noisy, and there could be tilt in the pictures, and you want to get rid of the noise, so you want to do this averaging where you get rid of the tilt, you do the rotational alignment, and then you average to get rid of noise and get cleaner pictures. Eventually, you use these pictures to reconstruct the molecule in 3D, but my focus in this motivation is just to get rid of noise in the 2D pictures that you take. So that's the context, but I'm motivating things with a cat. So let's be a bit more mathematical. So my space of images X is a subset of pixel intensity functions in L2 and L1. We have a notion of vanilla distance, which is the L2 distance. You integrate the square discrepancy between 2 images. So here I'm going to have them share the same origin, F and G. The core of the distance, the vanilla distance here, comes from the fact that the white fur is being compared with black fur, or black fur is being compared with noise, the cat is being compared with noise, and all these discrepancies are adding up to this vanilla distance, to this L2 distance between images. But then we have the rotational alignment distance, where you rotate an image G over the space of rotations in SO2. And as you rotate G, you're trying to minimize the vanilla distance between F and the rotated version of G. So you rotate G, you minimize the vanilla distance. And in essence, what that's doing is it's trying to have the pictures as aligned as possible. The white fur aligned with the white fur, the black fur aligned with the black fur, eyes aligned with eyes. And after you do this alignment, you take the vanilla distance, and that gives you the rotational alignment distance, DSO2. And when we did this with this other picture, H, even after we try to minimize the vanilla distance, there's still bad discrepancy present between the black fur of the cat and the noise, the white fur is still interacting with black fur, and that's still causing discrepancy even after we try to minimize this vanilla distance discrepancy by rotations. And it's in that sense that I was saying that these two pictures are nearest neighbors in some sense, and these are far neighbors. It's in the sense of DSO2 distance, this rotational alignment distance. And your goal is to average, rotationally align and average yourself with nearest neighbors with respect to this distance. Those are the images that you want to do the averaging with. So you want to do machine learning with this DSO2 distance. You want to do nearest neighbors with it. But the issue is that this distance is very expensive. Itself, it's expensive. The DSO2 itself is expensive because you're comparing two pixel grids and you're rotating one to match with the other. What does that even mean? How do you rotate a pixel grid and match it with another pixel grid? And you have thousands of pixels in the image, so it's making the distance itself expensive. But also nearest neighbors, doing it the naive way, where you compute the whole distance matrix, and you have to compute distances between all pairs of images. That's also an expensive thing to do because you have thousands and thousands of images. So doing nearest neighbors the naive way is expensive. So let's address the first problem, that the distance itself is expensive. And I'm going to follow what they do in Cryo-EM. What they do is they grab the space of images X and they feed it through a Fourier transform that spits out functions that are complex valued over the plane. This is what the Fourier transform looks like, not that it matters. Probably seen this before. And the key thing is that in Cryo-EM, they mathematically argue, and with common sense, that the Fourier transform in polar coordinates can be approximated by a finite expansion in a function basis that is separated into a radial function and into a trigonometric polynomial. The trigonometric polynomial has frequency k, and it shows up in the first indexed sum, k, and the radial functions has a double index, k and q, for extra radial functions to complete the basis, and the second sum is for the q index. And you have these coefficients a, f, k, q that are double indexed. But it's a separated function basis, and it's even better, it's an orthonormal function basis. And it has a name called the Fourier-Bessel orthonormal basis. And because it's orthonormal, that allows us to do some approximations. So let's start with the vanilla distance. The vanilla distance between two images, f and g, is the same as the vanilla distance between their Fourier transforms, because the Fourier transform is unitary. And because of this approximation, and because this guy is an orthonormal basis, we can approximate this Fourier transform distance by the finite dimensional Euclidean distance between the coefficients in this expansion. So we have the vanilla distance between two functions, and we approximated it by a finite dimensional distance between coefficients in a finite expansion in an orthonormal basis. And people found ways to compute these coefficients fast. Now let's turn into the rotational alignment distance, where you're trying to minimize the vanilla distance over rotations, where one function is being rotated. Well, I can do the same thing. I can apply the Fourier transform because it's unitary. I can take the Fourier transform of f, but I want to understand what the Fourier transform looks like when I precompose with a rotation. So, okay, I'll go here, I'll precompose f with a rotation. I want to understand what the Fourier transform looks like. You can show that the effect of this precomposition on the Fourier transform is a polar shift, polar angle shift, where the shift is given by negative arg-r, the counterclockwise argument of the rotation. And if I bring it to the front, to the coefficient, what that tells me is that I keep the original coefficients as they are, but the effect of r is given by a phase shift scaled with arg-r or negative arg-r. But there's also this k that is speeding up this phase shift, kind of like a k-fold speed up of the phase shift, and it depends on the index k of the coefficient, the first indexed sum. The index k gives you the frequency or the speed up in this phase shift that comes as from the action of r on the coefficients. So if I replace negative arg-r with alpha between 0 and 2 pi, I really have an approximation. I replace Fourier transform of f with its coefficient, and now I can replace the Fourier transform of g rotated with the coefficients of g phase shifted by e to the ik alpha, where k is the k index that shows up in the coefficient. It depends on that first index of the coefficient. And you're trying to minimize this finite dimensional distance over the one parameter alpha. This way you approximate the rotational alignment distance with this finite dimensional distance minimization. Okay, so to conclude the motivation, we approximate the distance, SO2 distance, the rotational alignment distance, with this finite dimensional distance of phase shifts. And these are weights. The k's are weights because it's a weighted phase shift. You have a multiplicative weight on the alpha depending on the index k. And that's what you call the weighted phase retrieval distance. When all the k's are equal to 1, that's what you call standard phase retrieval distance that many of you might be familiar with. But here my phase shifts have different weights based on the indices of the coefficients. That's why it's called weighted phase retrieval. And again, my goal is to do nearest neighbors with this distance because we wanted to do nearest neighbors with SO2. But yet again, this is still expensive to do. We approximated the distance by a one-dimensional minimization of finite dimensional things. So it's a bit easier to compute the distance itself. You can actually approximate it with a fast Fourier transform. But it's still hard to do this problem the naive way because you have thousands and thousands of images. So computing the distance matrix will still take a very long time to do. So it's still expensive to do nearest neighbors with this distance. But at least what I hope to show you with the motivation is that you should care about this distance, the weighted phase retrieval distance, and doing machine learning with it because it shows up in Cryo-EM and the Cryo-EM problem. So before I proceed with the rest of the talk, any questions so far? Okay. So for the rest of the talk, I'll focus on this distance itself. I'm not going to focus on any other part of the motivation. So if you missed some parts of it, that's okay. It's going to be about the weighted phase retrieval distance. So coming up, I'm going to show you that this distance is actually a metric on an orbit space of a certain group action. And then I'll transfer the nearest neighbors problem from the orbit space to Euclidean space through a quasi-isometry. And I'll tell you more about that. I'll show you that the previous Cryo-EM approach that's called the bispectrum is not a quasi-isometry. And then I'll show you why a recently proposed approach called the max filters is a quasi-isometry that transfers the nearest neighbors problem well from orbit space to Euclidean space. So I'll delve into more details. Let me start with the first two bullet points. So we want to see this distance as an orbit space distance. So I'm going to be a bit more mathematical in my language now. What I really have is a circle acting on a complex dimensional space, complex space of dimension d, and a theta in the circle acts on this d-dimensional vector with complex entries xj by phase shifting them, where you have weights kj integers that are attached to these phase shifts of each entry in the vector. So theta shows up in the phase shift, and these weights kj show up in the phase shift. You can think of this as a direct sum of irreducible representations of a circle, if you will. For example, I can have the first two entries of a 7-dimensional vector being acted on by e to the I theta. So here k is equal to 1, so you kind of have a 1-to-1 action. But the next three entries, I can have a speed up of k equals 2. So there's a twofold speed up on the phase shift. They get phase shifted much faster. And the last two entries, I can have k equal to 0, and they're not affected by the phase shift. That's just an example. And when we have a group action, we talk about orbits. So you think of X and all the possible ways it goes under the action of theta in the circle, and you collect those into a set, and you call those the orbit of X or bracket X. And when we have orbits, we have a unitary action. We also have an orbital distance. A distance between orbits. You create a metric space on these equivalence classes. And it's given by this minimization where you fix X and you let theta act on Y, and you minimize the Euclidean distance from X to the orbit of Y, essentially. And this is precisely the weighted phase retrieval distance, just repackaged as an orbit space distance where the action is given by these entry-wise phase shift as an action of a circle. So I want to do machine learning with this orbit space distance. I want to do nearest neighbors with it. So we have space of equivalence classes of orbits. So each point in the orbit space represents an equivalence class. And I have this orbital metric on these equivalence classes of orbits. And I want to do nearest neighbors. I want to pick a point and find its nearest neighbors. But the issue is, like I said, it's expensive to do this the naive way of computing all pairs of distances when you have thousands and thousands of points. But in Euclidean space, it's not expensive. You have a fast randomized nearest neighbors algorithm that people have come up with before, and there's papers on how to do nearest neighbors fast in Euclidean space. But we're stuck in orbit space, so what do? Well, I'm just gonna map the orbit space to Euclidean space under some map V. I'll transfer the nearest neighbors problem from orbit space to Euclidean space and do it fast there. Well, you better satisfy some things for this transfer to be successful. First, you want it to be fast, because the whole point of doing these things is this transfer is because we want to leverage a fast algorithm in Euclidean space. So this phi to begin with better be fast. And this phi better preserve distance as well, because you're transferring a nearest neighbors problem from a space to another. So you better have the distances preserved as much as you can. Another term for this is that you want phi to be quasi-isometric. And you can argue with just a bit of theory that the correct definition that you're looking for with quasi-isometry is the following. This is the correct definition you're looking for. Consider the following fraction where the numerator is given by the distance in the output. So the Euclidean distance between phi of x and phi of y in the output space, and you divide by the input distance between x and y, that's the orbital distance. You want this fraction to be bounded by a alpha that is positive on the left and beta that is finite on the right. And essentially what this is saying is that if 2 points start by being far away in the input, then they have to be far away in the output. And if they start to be really close in the input, then they have to be really close in the output. So you're kind of like preserving this sense of how far points stay far, close points stay close. And there's three terminologies I can attach to this. You can view phi as a frame operator in some sense, and then you call alpha the lower frame bound and beta the upper frame bound. You can view or you can use the terminology from phase retrieval and where they call alpha the lower stability bound and beta the upper stability bound. And the terminology that I use is bilipschitz. So here, if you multiply both sides by the denominator distance, this becomes a bilipschitz condition on phi, and beta is your upper Lipschitz bound, alpha is your lower Lipschitz bound. So in some sense, you can attach three terminologies to quasi-isometry. You can call phi a quasi-isometry or a stable embedding or bilipschitz embedding. These are all terms for the same property that this fraction is bounded above and below. So that's going to be our goal, to have a quasi-isometric embedding of the orbit space into Euclidean space. And that's where we're going to proceed towards in the rest of the talk. Any questions so far? Okay. So that's what I motivated for you so far. I showed you that the weighted phase retrieval distance is an orbit space distance, and our goal is to transfer the nearest neighbors problem to Euclidean space via quasi-isometry, where this fraction is bounded above and below. Now let's go to the next step, which is telling you about the previous approach that's called the bispectrum. Okay, so that's our objective. Our objective is a fast embedding that is quasi-isometric. But before I proceed, I just want to cover a small technical thing, kind of like a lifting triangle. So we have this orbit space mapping to Euclidean space, and I can complete this into a triangle where you see S1 acting on complex space, and we have this projection map or orbit map taking X to its equivalence class bracket x in the orbit space. And the idea of having a phi whose domain is orbit space, who acts on bracket x, is the same idea as having a phi whose domain is complex space being acted on, as long as this phi is invariant to the group action, meaning as long as phi of theta x is the same as phi of x for all theta. In other words, this phi whose domain is complex space is constant on equivalence classes. So you can think of this as a topological quotient triangle, where if you start with an invariant phi, then you can lift it to a phi mapping from the orbit space. And if you start from the orbit space, you can pre-compose with the orbit map to get an invariant phi, just a lift and project triangle. And the only reason I'm mentioning this is because I'm going to introduce the bispectrum approach with the invariant in the invariant sense. Okay, so the initial approach in Cryo-EM by Zhao and Singer in 2014, you do the following. Let's consider an X, and let's say you have the action of theta on it that's given by phase shifts with different weights. And what they do is they take triplets of components in the vector, and they conjugate the third component that they take. And when you do that, the group action influence is as follows. That's the original triplet, xi, xj, xm, with xm conjugated. And the effect of the group action is given by a phase shift of this cubic monomial, but the weight is given by ki plus kj minus km. And you want the monomial to be invariant. You want this monomial to be invariant. So you better have ki plus kj minus km sum up to 0. In other words, you better have km equal to ki plus kj. And that's what they do. They say, consider phi, whose components are cubic monomials with the third term conjugated. And the indices are chosen in such a way that the weights, km, is equal to ki plus kj. This way, all of these monomials are invariant, and you get an embedding of the orbit space. So that's what they call the bispectrum embedding. And one thing you'll notice is that it's differentiable in the real sense, not in the complex sense. It's real differentiable because it's a polynomial. And here's the first result. If you're differentiable, you can't be quasi-isometric. There's special cases where you can, when your action is free on the sphere. But in weighted phase retrieval, you can't have differentiability and quasi-isometry at the same time. If you're differentiable, you're not quasi-isometric. And this is, I proved this result for infinite group actions in general, but this has been proven previously for finite group actions by Cahill, Mixon, and Everson. And I generalized their theorem into infinite group action by using some geometry of the orbits. But the idea is differentiable implies not quasi-isometric. Bispectrum embedding is differentiable, therefore it's not quasi-isometric. And for the rest of the talk, I'm going to be telling you about the quasi-isometric approach. Any questions so far? Okay, so for the next approach, it's the, overview. Right, so I showed you that the bispectrum is not a quasi-isometry, and now I'm going to show you that I'm going to introduce something called max filters, and I'm going to show you why it is a quasi-isometry. The max filter approach that was in 2022, introduced by Cahill, Everson, Mixon, and Packer. I'll motivate the approach. Let's do some visualization. Let's say you have a sphere in 3D. When you have a point X, it has an orbit, bracket X, and my action is unitary, so it preserves norms. And therefore, when you start on the sphere, you stay on the sphere. That's why the orbit of X is on the sphere. And I can have another orbit, Z, somewhere else on a different sphere. Doesn't need to be on the same sphere, but it's in its own sphere centered at the origin. And there's something called the cosine law in linear algebra. The square norm of x minus z is the norm of x squared plus z squared minus twice the inner product between x and z. And here this is like the real part of the Hermitian product between x and z. Okay, I can do more. I can have theta 1 act on x as in this law, and then can have theta 2 act on z. But then I have a unitary action, so I can get rid of theta 1 and theta 2 in the norms. I can do more. I can take a minimum on the left, a minimum over theta 1 and theta 2, and I can take that turns into a maximum on the right because of this negative sign. And what this is saying is that you're minimizing the Euclidean distance between the orbit of x and the orbit of z. So you minimize the distance between them as sets, and you get the straight line minimizer between the minimizers. But minimizing Euclidean distance between two orbits is the same as maximizing their inner product. This is what this equation is saying. The minimizers of distance are the same as maximizers of inner product, and the minimum and the maximum are related by this equation. So the thing on the left, the minimum distance, that's the orbital distance. That's a weighted phase retrieval distance. And the thing on the right is what you call the max filter between x and z, and it's denoted by this double angled bracket between the orbits of x and z. So you minimize distance, but then you measure the inner product between the minimizers. That gives you the maximum inner product between the orbits. That's what you call the max filter. You maximize inner product. And what they do is they view z as a measuring device, also known as a template, and then you view the max filter as a measurement. You measure x with respect to z. And then you create multiple measuring devices. You put z1 here in space, z1 somewhere, z2 somewhere else, up to zn over there in space. And then you take measurements of x with respect to each measuring device and you lump them into a vector. How do you take measurements? You minimize distance, and then you take an inner product between the distance minimizer. Minimize distance to this other guy, take an inner product between the distance minimizer. Collect them into a vector of measurements. There's n of them, and that vector of measurements will be your phi of x, and you call that the max filter bank. And a variant of their conjecture in weighted phase retrieval, at least, if you have enough measuring devices, if n is at least 4D minus 3, so n is the number of measuring devices or the dimensionality of the output space of this phi, or the codomain of phi. If you have enough measuring devices, at least 4D minus 3, let me remind you what D was. My action was acting on a complex vector with D entries. So it's the complex dimension of the space being acted on. If I have enough measuring devices, then phi, the max filter bank, will be quasi-isometric for generic tuples of measuring devices. Just as long as you have enough of them, you can pick them generically. And you can think of that in a semi-algebraic sense, where the dimensionality of the bad set is low. Or you can think of it as the set of bad tuples forms a measure zero, has measure zero, if you wish. So that's a conjecture. And what we do is we turn this into a theorem, and with the proof techniques that we have to multiply by a k max, which is the maximum weight of the action, the maximum speed up that results in the action. And with that, that turns into a theorem. And the K-max shows up because of a pigeonhole principle that I will illustrate later. So a few things before I proceed. The rest of the talk will be dedicated to give you a sketch of the proof for the lower Lipschitz bound, why the lower bound exists, proving this theorem. The upper Lipschitz bound has been previously established in the original paper, and it's a bit easier to deal with the upper Lipschitz bound when it comes to max filter banks. It's the lower Lipschitz bound that is extremely hard to deal with. A few more notes. The max filter one reason I defend them is because they are component-wise convex. So you have subgradients for the second component, and you can use a subgradient method to train your measuring devices. So it's a trainable embedding, and you can create a loss function and then train measuring devices to be good with respect to that loss function. And this is something they've done in 2022 paper, and they have some machine learning examples where they train the embedding before using it. It's component-wise convex, and it has the potential to be quasi-isometric for more general group action. It has been shown to be quasi-isometric for finite group actions. You can generalize the definition of the max filter for any group action. Doesn't need to be weighted phase retrieval. And it has been shown that for finite groups, you get quasi-isometry most of the time. It's still open for infinite groups. I'll discuss that later. Also, from a computational standpoint, some max filters are hard to compute. But in the case of weighted phase retrieval, you can approximate it with a fast Fourier transform to get the max filters. So it has potentials to have applications in Cryo-EM, but I'm focusing on the theory in this talk. So again, the rest of the talk will be about the lower Lipschitz bound proof. It's a proof sketch. And any questions so far before I proceed? Okay, so our goal is to establish a lower Lipschitz bound. What does that mean? Let me remind you. We had this fraction where on top you have the distance in the output, and on the bottom you have the distance in the input. And we want to show that this is bounded away from 0 through this alpha. Without loss of generality, this is symmetric in x and y, so I'm going to assume that y has less norm than x. And I'm going to multiply and divide by the bigger norm of x. And you can use scalar homogeneity to feed this into the inputs. And really what you end up rewriting the fraction as, you can see that the first component here is a unit vector. And the second component, because y has a weaker norm, that's in the unit ball. So from now on, I can replace x with its normalization and assume that x has unit norm and y is in the unit ball. So I can erase everything and just have that assumption. Also, I need to assume that my x is unequal to y. This is part of the fraction. Otherwise, the denominator will be 0, which doesn't make sense. I'll proceed by a proof by contradiction. So if there does not exist an alpha, then I can keep choosing huge m in such a way that the fraction can be made worse and worse than 1 over m. So I can keep finding this xm and ym, these bad orbits that make the fraction so low that it's lower than 1 over m. It's positive fraction, so really this is saying that this fraction is converging to 0. It keeps getting weaker and weaker and weaker with the sequence of xm and ym. So really I have a sequence, xm and ym, such that the fraction, when you plug them into the fraction converges to 0. It's getting weaker and weaker. And again, my x's are in the unit sphere by assumption, and my y's are in the unit ball. So I can take subsequences, compact sets, right? I can take subsequences and assume that xm is converging to x and ym is converging to y. Okay, let's remember what we're doing. Our phi was a vector of measurements with respect to a bunch of measuring devices, and I had n of them. And my hypothesis was that I have enough measuring devices, n is bigger than k max times 4d minus 3. So let's keep the hypothesis in mind. Okay. Now we'll do an analysis, right? So I have xm converging to x, ym converging to y. I'll do a case analysis on the orbits, on the limiting orbits. So the first case I'll deal with is if the limiting orbits are not the same. So you can think of the xm's as a bunch of circles converging to the circle of x, ym's converging to the circle of y, and then the resulting orbits, the limits, are not the same. So that's the first case. That means that the distance between the limits, orbital distance, is positive. which means that the denominator is bounded away from 0 by continuity. But then the fraction is converging to 0. That means the numerator is converging to 0 because the denominator is bounded away from 0. We conclude that the numerator converges to 0. But then by continuity, that tells us that phi of x is equal to phi of y, because the numerator is a norm of difference. So in the limit, you get this equality, which really tells us that phi is not injective. But then we have a theorem that says if you have enough measuring devices, at least 4D minus 3, then phi is injective. But we have k max factors of limit. K max is at least 1. So the hypothesis of the theorem is satisfied, which means phi is injective, which contradicts the statement that phi is not injective. So that's a contradiction. Any questions before I proceed? Okay, so that's the first case. Injectivity is what solves it. Now, what if x and y had the same orbit? Okay, that's case 2. Then that tells me that y is a translate of x. Y is equal to theta x for some x. And then here I should be multiplying by theta inverse. There's a typo here. If I multiply by theta inverse this sequence, ym converging to y, my fraction is invariant to the group action. It only depends on the orbits. So it doesn't matter if you change up ym with a theta. We can keep it as ym anyway. And if you multiply theta inverse with y, then you can turn it into an x. So it really tells me that I can assume that my xm and ym are converging to the same point, not just the same orbit, but the same point because of invariance. Okay. How do we break this? I'm going to show that this fraction is bounded away from 0. That's my goal. I'm going to break convergence to 0. So given sequences xm and ym that converge to a shared point x in the sphere, I want to show that this fraction is bounded away from 0 after I take subsequences. This way I break the convergence to 0. You're not going to get weaker and weaker. You're bounded away from 0 after I take subsequences, and that will be a contradiction. So that's my goal. Any questions about the goal? Okay, so the game plan will be to give you 2 preliminaries before I go back to this statement and tackle it more. First preliminary, phi is a bunch of max filter measurements stacked up on each other. The max filter is a maximization of inner product between 2 orbits. But I've shown you before with the cosine law that maximizing inner product between 2 orbits, what you do is you first minimize distance between the 2 orbits, and then you take the inner product between the distance minimizers between the orbits. But orbits are manifolds, so we want to understand distance. I want to understand the geometry of the max filter. Therefore, I have to understand the geometry of distance minimization to a manifold. So that's going to be the first preliminary, distance minimization to a manifold. I have a manifold M that looks like a parabola in 2D, and I have a point Z, and I want to minimize distance from Z to M. So I bring the point as close as possible, and I call that P of Z, the projection of Z on M, and I'll call it X. And this projection is orthogonal, the projection line at least, is orthogonal to the tangent space at X has a 90-degree angle. I want to understand the fiber of X under this projection. So I'm going to pull Z back as much as I can, keeping it in the fiber. The bad point happens on the y-axis where we have symmetry, because that's an ambiguity point. Z does not have a unique minimizer anymore. It has 2 distinct minimizers. So the projection map from Z to M is not well defined on this point in the y-axis. So my fiber, I'm going to truncate it at this ambiguity point and put an open interval there. So I'm constructing the fiber of X, the points that project uniquely on X. All of these dashed points, they project uniquely on X. They have a unique distance minimizer given by X. That's the fiber of X. And if I go to the right, I can keep going to infinity. And all of these guys project on X as a nearest neighbor, unique nearest neighbor. That's the fiber of X under the projection map to Z. And you call that Vx, the Voronoi cell of X. And it forms a 90-degree angle with the tangent space to the manifold at X. And you can keep going. You can do this for any point, and you can keep constructing Voronoi cells at each point until you expand them until you hit ambiguity, expand until you hit ambiguity, expand until you hit ambiguity. And these form fibers. And the ambiguity line is this guy on the y-axis that starts from a half and goes up all the way to infinity. The half comes from the fact that this m is the graph of x squared. And here's a cool fact about Voronoi cells for any manifold M. First, they are disjoint, and their disjoint union forms an open and dense subset of your ambient space. In this case, it's R2. Their complement is the closure of ambiguity points, is dimension deficient. You can think of it as having measure 0 if you wish. The bad points have measure 0. Or if your manifold is semi-algebraic, then you can show that the complement is semi-algebraic, and dimension deficiency means that the highest dimensional subset of the semi-algebraic set is dimension deficient. If you know the semi-algebraic language. Otherwise, just you can think of it as measure 0 set. And that's a preliminary on Voronoi cells. They are the fibers of the projection on M, where you have a unique nearest point to the manifold. Let's go to the second preliminary, stabilizers. I'll illustrate this with a small example, two-dimensional complex space. The first entry is being acted on by e to the I theta. The second entry is acted on by e to the 3I theta. How do we visualize this? Well, I'm gonna make the vector into two complex planes, two separate complex planes. And my x is gonna have arg0 in both of them, but different radius in this example. And I have theta acting on x. Let's see how theta acts on the first component. They act one-on-one. They go together with the same speed. And that's because I have e to the I theta, which acts with the same speed. But for the second one, I have 3 times the speed. So it's going faster. When theta completes 1 revolution, the green orbit only completes 3 revolutions. It's going faster. So this guy is going 1-to-1, and the green guy is going faster, kind of like 3-to-1. And now I want to understand what happens if I don't have a blue portion, and I only have a green portion that is fast. And I want to visualize this in 2D. This is a 4-dimensional space, but I'm projecting on 2D. So again, the green orbit is going fast, right? I'm assuming this orbit does not have a blue portion, so it's going fast. Now, what happens if I perturb the blue portion and give it a little bit of radius? Then this is a perturbation of the green point, and it gives me a blue point. And then what happens if I act? Well, it's the orbit of the blue point should also be a perturbation of the green orbit, the orbit of the green point. So when I act, it should look like the same thing as the action of the green orbit, but just perturbed. So I have to go 3 times around. But the blue portion goes one-on-one, which means it should be free. It doesn't self-intersect. Here, there's self-intersection in 2D after I project from 4D. But in 4 dimensions, this orbit is not self-intersecting. And I'll show you a picture in 3D where actually it's not self-intersecting. But in 2D, I have to draw it with a self-intersection. But the blue orbit tries to follow the green orbit because it's a perturbation of it, but it also has a free portion, this blue portion that is free. So it tries to avoid self-intersections and repeating itself. Namely, when you draw the Voronoi cell of the green point, it intersects the blue orbit in 3 points. three distinct points, because the blue orbit doesn't want to repeat itself, but it comes back 3 times trying to follow the green orbit. So it intersects the Voronoi cell of the green orbit in 3 distinct points. And that's a more general thing. When you have a group action and you have these weights kj, then the highest weight kmax tells you the maximum cardinality of the intersection between a free orbit, y, the blue orbit, and the Voronoi cell of the green orbit that repeats itself. In the case of kmax, the green orbit would have speed kmax. So we have a hold on the cardinality of this kind of local perturbation intersection between the Voronoi cell of the ambiguous orbit with repetitions and orbits locally that don't have repetitions. They try to avoid self-intersection. I'm assuming here that I have an e to the I theta somewhere, but you can do some technical argument where like you can just assume you have e to the I theta or deal for the general case. Not a big deal. Any questions about this before I proceed? Okay. So that's the second preliminary on stabilizers and how they look locally near Voronoi cells. Now let's remember our goal. We had sequences converging to a shared X, and we wanted to show that this fraction for these sequences, this output divided by input distance, is bounded away from 0 after you take subsequences, because we want to break convergence to 0. I'm going to turn things into 3D. Oh, before that, here, right, I have XM and YM, and they're converging to X. The X is pink, and the XM is the green guy. The YM is the green guy. They're converging to X. One thing I can do is I can delete orbits. Because my fraction is invariant, I don't care about the rest of the orbits. I'm only going to care about the Voronoi cell of X and how it intersects with the orbit of XM and orbit of YM. And I'm free to choose XM to be any of these 3 points and YM to be any of these 3 points because my fraction is invariant. So it doesn't matter which XM and YM you choose. And these XMs and YMs are still converging to X. So the analysis is going to be inside a Voronoi cell, is what I'm trying to say. Let's turn things into 3D. So I have the orbit of X, and I have the Voronoi cell, which looks like a plane, going all the way until the center of the circle. I have an orbit of XM, and it's converging to the orbit of X. Here, you don't have self-intersections. In 3D, I'm able to draw it without self-intersections. And as I said, we can delete the orbit, so I can assume that these 3 points, I'm free to choose XM between these 3 points that converge to X. And I have YM as well, and I'm free to choose YM between these 3 points that converge to X. And even better, I'm going to delete 2 points in XM, and I'm just going to make a choice for XM. And I'm going to keep myself a bit free with YM, which points I choose. Then we have a measuring device, ZI. ZI also has this 3-fold rotation around X, and it has to come back at different points. So these 3 fibers, these 3 hair strands, are connected somewhere else in space. They are part of a single connected orbit, but locally they look like 3 hair strands for this measuring device. And this XM, we want to understand phi of XM. I want to understand the measurement of XM with respect to ZI. So I do distance minimization with respect to ZI, but the distance minimizer may not be ZI itself, but a perturbation of it. But in the limit, it's okay. I can approximate the max filter between XM and ZI as an inner product between XM and the point on the Voronoi cell instead of this perturbation point. I can do this approximation. I can assume that XM is closest to ZI, and I take the inner product with that instead of this. And here I'm swiping so many things under the rug. So in order to be able to do this approximation where you don't care about this small perturbation from ZI, you have to look at the hair strands locally, view them as a fiber bundle themselves, and then take a quotient, and that quotient is a Riemannian submersion, and you do analysis for the geodesics of that Riemannian submersion, and you arrive to the conclusion that, okay, I can now approximate the max filter between XM and ZI as the inner product between XM and the ZI on the Voronoi cell instead of this perturbation. So I'm sliding a lot of things under the rug with this approximation. And for YM, what I'm going to do is I'm going to get it closest to ZI instead of the other way around. I'm going to move YM to as close as possible to ZI. Then the max filter between YM and ZI is given by this inner product between the closest points, GI, YM, and ZI. Again, I'm swiping many things under the rug here. This is an approximation. And then phi of XM and phi of YM, the ith entry gives you the difference between the ith measurements. And the ith measurements have the same right-hand component, ZI, so I can keep it as a right-hand component and then subtract the left-hand components with an approximation. And my goal was to look at this fraction where I have the phi vector, take a norm, difference norm. So I'll do this approximation and take a sum square of these entries, the entries of the difference. So that's why I have a sum square in the numerator of the entries of the difference approximated by XM minus GIYM comma ZI squared. And the distance between XM and YM is so small. It's the worst case distance, the smallest distance you can get between XM and YM. So it's okay to relax it to the norm from XM to GIYM to make it match the numerator. And with this relaxation, I'm making the distance bigger. This norm is big. And I can replace equality with an inequality bigger than or equal to. But that's okay because I want to show this guy is bounded away from 0. So it's okay to show that the right-hand side is bounded away from 0. So like, it's okay to replace the distance with a bigger thing as long as the right-hand side is still bounded away from 0. And with that, that's my goal. I'm going to show this guy is bounded away from 0. And it's almost looking like a frame operator. But the issue is that I have different GI for different I. I don't want that to happen. So the dimension of Vx is 2D minus 1. 2D is the real dimension of space because I have D complex dimensions. And I'm losing one dimension from the orbit of X. So the dimension of Vx is 2D minus 1. And I have enough measuring devices by hypothesis. I have so many of them that they kind of form a pigeonhole principle argument. So Kmax is the number of intersections with Vx, with Ym. It's the number of holes. I'm viewing GI, Ym as the holes, and I want to fix the GI. I don't want it to change. I want GI to be fixed. So I want so many of the I's to go to the same hole. And the number of holes that I have is Kmax. And I'm going to have so many ZI's that go to the same hole that I'm going to call W, Ym. That's the hole in the pigeonhole principle. And I'm going to have so many ZI's that I have dimension Vx of them going into the same hole and acting on the same unit vector with this pigeonhole principle. And now they all have the same shared unit vector. And this has a lower frame bound as long as the ZI's are linearly independent, which you can do generically. Linear independence of the ZI's that come from the pigeonhole principle, you can achieve that generically as long as you have dimension Vx of them. I guess, sorry, it should be spanning, and it should be spanning, not linearly independent. That's a typo, right? As long as you have dimension Vx of them, then generically they will be spanning, and then you have a lower frame bound, and then this guy will be bounded away from 0 now that I have a shared unit vector being acted on. And the unit vector shared is coming from the pigeonhole principle. If you plug the numbers in, they will not arrive to 4D minus 3. They will arrive to 2D minus 2 instead. But then you need more templates just to assume that the ZI is in Vx to begin with. This is not, you don't get this in a straightforward manner. You need enough templates to get there. And that's where the 4D minus 3 comes in. So yeah, the Kmax comes from a pigeonhole principle where you try to have them share the same unit vector. Well, I hope this was just like an illustration of what a proof can look like in this setting. Might have went a bit fast, but in summary, these max filter banks, the paper addresses a more general setting where we show that it's quasi-isometric for orbifold quotients, and weighted phase retrieval is an example of an orbifold quotient action. And there's so many open problems left to do. It's still open whether these max filter banks are quasi-isometric for all group action quotients. We've only addressed the orbifold case in the paper. And what are better and faster quasi-isometries for weighted phase retrieval? It has applications in cryo-EM. So it's also open to compute really good quasi-isometries. The max filter banks are an example, but what are other examples? So I'll leave you with that, and I'm happy to answer any questions. Thank you very much.
All right, let's smash that reaction button.